Hi, this is Miss Logan. Today I'll be talking about friction and springs. So I'll be going through the equations for both of these and how to solve them. Okay, so friction is when a force is present whenever an object is moving across another object. The amount of friction can be caused by the material of the surface and also the normal force. So the material of the surface, if something is more rough at the microscopic level, it's going to have more friction. Normal force, though, we'll talk about what that is in a minute. So there are two types of friction. The first one is static friction. So this is when an object is not moving. So this is when something is sitting on the ground and I am pushing it to get it started. Okay, so I keep pushing it and finally there'll be a point where it starts moving. So at this situation, when it starts moving, I'll have kinetic friction. So something that's unique about kinetic friction is that it's always less than static friction. So this makes sense. If you think about pushing something, it always takes a lot more effort to actually get it started than when you're actually pushing it. So this is really why kinetic friction, movement, is less than static friction when something is still. Okay, so the general formula for friction is force of friction equals mu force normal. So mu is a number between 0 and 1. Okay, we'll talk about it in class, but mu is really just a ratio. So it has no units, and like I said, it's always between 0 and 1. Force normal, we'll get to in a minute. Force of friction is always in newtons as well. Now, on this slide, there's two formulas for static friction and kinetic friction, but they're really just the same. The only difference between the two of them is the notation here. Now, we're talking about force of friction. We have force normal, and we've talked about force normal. Force normal is my support force. So, when something is sitting on something else and there is no angle, my force normal is equal to my weight. And my weight is my mass times my gravity. Now this changes when we're at an angle, but we won't be covering that. But when we're looking for force normal, it's always weight times gravity. So we can actually rewrite this equation. Force of friction equals mu mass times gravity. Okay, so let's do a problem. Gabe is pushing a refrigerator box that has a mass of 135 kilograms. If the coefficient of static friction is 0.47, what is the minimum force he needs to move the box? So we have force of friction equals mu force normal, and force normal is equal to mass times gravity. So I can do 0.47 for my mu, 135 for my mass, and 9.8 for my gravity. So I'm going to get a minimum force to get this started of 621.81 newtons. Right, the second part of this lesson is going to talk about spring force, which we also call Hooke's law. So when I put weight on a spring, it will be extended. Okay, we know this, and there's actually a relationship that we can look at between these two. So Hooke's law tells me a force is equal to K times delta X. So F is going to be my force. And sometimes when we're looking at springs, this is going to be the force that's actually on the spring. So we have a spring, and then we have some type of mass that's holding on it, and that would actually be our force. So we have force times K, and this is my spring constant. So kind of like mu, this is a ratio. So this is always in newtons per meter. So this is something you're either going to look for or it's going to be given to you about that particular spring. Delta X is how much the spring stretched. So sometimes when you see this written out, you'll actually see X. I like to use delta X though because it reminds us that we're looking for the stretch of the spring. All right, so a spring rests with a length of 6 centimeters. The spring has a mass of 4 kilograms that is placed on the spring and it moves to 8 centimeters. So let's draw this out. So first we have the spring is just sitting there and it's 6 centimeters. And then we put a mass on the spring and it goes down to 8 centimeters. What is the spring constant of the spring? So I have force equals K times delta X. So the force is actually this weight, okay? But before we do that, we need to actually solve for K. So I'm going to rearrange this equation. So I have force over delta X. Now, it's important to note that this force isn't just 4 kilograms. It's actually the weight. So when I'm looking at something on spring force that's hanging, I'm always looking for the weight. So 4 times 9.81. And that will give me my force on that spring. So it's 39 newtons. For delta X, we have to look at how much the spring stretched. So it went from 6 kilometers to 8 kilometers, which is a stretch of only 2 centimeters. Okay, so I have my force, which is 39, over delta X. So delta X needs to be in meters. So I actually need to change this 2 centimeters into meters. Putting that over 0.02 meters. So once again, to recap, this force I got from the mass that's hanging, getting its weight, which I went over in a previous slide, and delta X is how much it stretched in meters. So I'm going to get a spring constant of 1950 newtons over meters. So make sure you've taken notes on all of these different concepts, and we'll be using them in class, in labs, and practice problems.